Welcome to this webinar, which is focusing on unlocking the industrial-grade FDM using ADDCAAM and REALvision Pro. So the goal is really to make stronger print, reduce the porosity, and to do all of that by software with a smarter way of slicing. So let's go with introduction. I mentioned before that the webinar is being recorded, and that there will be a Q&A session at the end. You are more than welcome to ask questions during the webinar, and we will address all the answers at the end. So first, let's present ourselves. So my name is Jeremy. I'm the founder and CTO of Created Real. And Created Real is a software company based in Aalborg in Denmark.
Dan Saberton. I'm the engineering manager at Addman. I'm located in Florida in Fort Myers. Addman is a additive service provider as well as a engineering firm.
All right, so a little bit about Created Real. The company was founded back in 2009. We are more than 22 experts in 3D printing technology, developing the core slicers. So we develop core slicing technology, so really the pathfinding algorithm and every core component of the slicer. We have a commercial product called REALvision Pro. You're going to hear much more about this later. And we provide a white labeling slicer for industrial 3D printer manufacturers, so like 3D System or Meltio. It's branded with their name, but we are behind with the technology.
So a little bit about Addman. We were founded in 2020. We've got 8 different sites across the U.S. We are solely a U.S. company at this time. We do everything from engineering and development, from metal to metal and polymer additive, CNC machining, injection molding. So we've got quite the umbrella of different technologies within our company.
And we'll start talking a little bit about what are the challenges in 3D printing. So this is the technology adoption life cycle of Gartner, and every technology goes through those stages. So at the beginning, you have the hype. Everybody gets excited about the technology. Then there's a moment where there's a lot of deception. In 3D printing, it's usually people buying a very low-cost 3D printer and expecting result of a 3D printer that costs many millions of dollars. And then slowly, the technology finds its place, and then you can reach the plateau of productivity. So in 3D printing, we had this stage where we are moving from prototyping towards actual product. And this happens application by application. And you need to actually find the key elements that are missing to be able to make that transition. So this is really what we're trying to do here. So what are the challenges in FDM printing? Well, the struggle is really linked to the technology itself. So in FDM, you're creating the parts layer by layer, but you're making these beads that you deposit. And even so, the parts are extremely close to injection molding on the XY direction, you end up with a very weak Z-axis bonding. So it means that you have a limited structural integrity on the part, and they fail usually through the layers. You will, if you stress a FDM printed part, you will usually break it through the layer, the Z layer. There's also porosity issue because the beads, when you print, they are not perfect. I mean, they are not square. They are more like round, and then that leaves some gaps between the beads. And at the end, you end up with a part that is not isotropic, and you have an inefficient load distribution. So you have to be able to think how you oriented your part. So how do you go from, how to take FDM from prototypes to actual production of part? So FDM is ideal for prototyping, no doubt about this. It's very fast to print. It's cost efficient. You can validate a design quite quickly. There's tons of material available thanks to injection molding, so you have access to all the material that has been made for this. And today, the price is very affordable, meaning that everybody have access to low-cost 3D printer. Now, why does it fall short? That's what we described just before, a weak layer bonding, porosity issue that creates basically those limitations on the mechanical performance of the part. So it's really, if you could move a little bit on the mechanical performance, you will move a lot in terms of what applications are now becoming moving from prototypes to product. So when you usually use FDM, you have to think on how to orient the part so that you take advantage of the strength on XY, and you hide the problem limited to the Z axis. You have problem with infill, how to and post processing also on FDM. So with all those problems in mind, this is where Addman had the big idea. So I will let Dan talk about this.
Thanks, Jeremy. So really the big idea here is to increase the strength of the parts through software. A lot of developments have been done through a lot of different companies to increase the strength of materials. You might get like maybe increase 5-10%, printer technology can also increase the strength of parts. But really where all these FDM parts fall short is in the way that you actually build the parts. So by optimizing the tool path is really how you're going to increase the strength of the parts more than anything else. So there's really two main features in the software that we use to increase the strength of the parts. So the first one's the interlace technology, and this is where we use the shifted layers to basically stack the beads in such a way to where whenever the part fractures, the force isn't distributed through a straight line through that XY plane. It has to travel and bend all over the place. So that really increases the strength of the part. Not only that, by stacking the beads in the way that we do, we're greatly reducing the amount of porosity in these parts as well, which of course also increases the strength of the parts. Now, another interesting thing that we've got with these parts as well, a lot of these 3D printed parts are not solid, right? A lot of them have sparse infill on the inside. So what we do is we actually lock that infill structure into the outer walls of the part. And this technology is what we call interlocking infill. So essentially what we're doing here is we're adding an extra wall for every other layer so that we can sort of sandwich the edges of that infill structure into the walls of the part, making a more monolithic type structure. So here on the right side, if you take a look at this diagram, this is sort of, how we build the parts. So you're going to start off with a half bead, a half height bead on basically every other pass on your first layer. Then after that, you're going to use full beads for the rest of the whole print. And essentially what those two half beads do for the rest of the print is they stagger the beads for the rest of the print, and then you sort of get this offset bead layout as you see here. And of course, this is going to really increase the layer adhesion by weaving those layers together. Also, it's going to get rid of a lot of the voids inside of your parts. And then also, really distribute the load throughout the part rather than just shearing right across that XY plane. So what this is going to do is it's, as Jeremy said before, it's going to open a lot more opportunities to create real production end-use type parts using FDM technology. So really the journey with Create It Real, there's a lot of different ways that you could have gone about this. We could have gone through some real hokey scripting methods and stuff, and through some other open source type softwares, but we really wanted to make a very robust professional approach to releasing this software, And so what we did is we partnered with Create It Real to have them develop this technology on their platform, and so this is going to really expand the accessibility of the software to a much larger group of people. It's going to create a very user-friendly and easy-to-use software that's easy to learn, that you don't have to be some kind of scripting master to figure out how to use it, right? And then also, it's very simple to use. And then also, we want to make this technology available to everybody in the FDM sort of user group, right? So we want to make sure that everybody can use this and utilize the technology in a very easy and simple way, and really take out all the complexity of it by creating a nice user-friendly interface with Create It Real. So really the idea of the interlace technology here, again, you're seeing all these different pictures, but here what we're seeing, if you take a look at this red line, this is representing, your shear path of the fracture through the part. If you look at the blue arrows, see that this is kind of like a free body diagram of the forces that we're putting on the part in sort of a shear type scenario, right? Now, most of your FDM parts, they're going to have less than 20% strength in the Z direction of the parent material, and breaking along that XY plane, makes these parts very weak. So if you look at the bottom picture, you see how this force has to travel and change all these different directions as that fracture travels through the part. And anytime you make that fracture change direction, that's going to drastically increase the strength of the part. Because if you're just essentially, in your standard FDM printed parts, that XY plane is just a zipper, right? So as soon as that break starts, it's going to go right through the whole part along that plane. And as many of you know who have made FDM parts before, if you ever break it, you'll always see that it breaks along that XY plane for the most part. So where does the strength come from with these parts? Of course, actually, we've done a lot of testing on all these parts in a bunch of different ways, and we found that actually the strength of these parts is increased in every scenario: shear strength, tensile strength, and fracture strength. One interesting thing that we found out was that this overflow is sort of required with these parts. So essentially, you're increasing the amount of material that you extrude in these parts because the way that we lay down the beads, we're filling in more of those gaps. So essentially, we have to extrude more material in the same amount of volume as a traditional print. So it's going to make a denser part and a part with much less porosity. So if you take a look at these arrows here, you'll see the interlace contour that's sort of pointing to the bead stacking method that we use. And this is sort of like the outside of the part, right? Your shell or your walls, as we could say. And then also we've got the interlocking infill where, we're making that extra wall every other layer. And then also, as Jeremy will show you in a later video, we've got a interlace infill, which essentially uses the same technology as the interlace contour, except you're essentially filling the part with a solid pattern using the interlace technology, and you can actually control the direction that that's pointing. And then, of course, we want to make sure that when we print these parts, that we make sure that we can maintain a good surface finish on these parts as well. And another interesting technology that we found out was this gradient flow top and bottom. So whenever you print over top of a sparse infill, a lot of these those layers, they're going to sag into the sparse areas of the infill, and it takes a lot of layers until you're actually able to get a solid layer. And so what we can do is actually increase the amount of extrusion on those first layers above the infill so that we can reach a solid layer in much fewer layers than a traditional print. So if you take a look at how these parts break, comparing your traditionally sliced parts and the ADDCAAM parts, as I said before, the traditionally parts, they're always going to break along that XY plane. So if you look at the picture on the left, we're only, our break is only traveling through maybe 2 or 3 layers on this part, and for the most part, these fractures are very planar. And if you look at the ADDCAAM part, you can see there's many different layers that the fracture occurs through. Most of them, which you can't really even identify a layer that the fracture occurred through, because it always changes directions as it goes through the part. So the break that you're seeing here is going to look a lot more like a homogeneous injection molded part than your traditional FDM part. And so I do have a quick video I would like to show that shows sort of, the basic functions of ADDCAAM, and this is going to show the interlace technology. It's going to show the interlocking infill. And then it's also going to show the top and bottoms of the part as far as using the ADDCAAM technology for those. So let's go ahead and play this video, and you'll see there's some call outs that point to all the different areas of the parts that use all these different technologies. So as you saw, you could see where the infill was sort of sandwiched into the walls, sort of creating that monolithic structure. We use sort of a concentric pattern on the tops and bottoms to make sure that we can get that the offset bead structure on the top and bottom of the part. And then, of course, we use the same bead stacking method in the walls as well. And then I also have another video I'd like to show that sort of highlights the gradient infill. So this is going to show some of the options that we choose. So we can define a flow for our first layers, and then the very top layer we can define a different flow, and it's sort of going to have a gradient flow from that first top layer to the very top layer. And there's a really interesting feature inside REALvision where you can visualize the part based on the amount of material flow. And so if you'll look at this video when I show it, it's going to show how the color changes from a very dark green to a lighter green, and that's going to represent the amount of material that's being extruded for those beads. So let's go ahead and take a look at this. So that sort of gives you the idea of how this gradient flow sort of really gets you a much denser top surface. And of course, you can use the same technology for bottom surfaces as well. For example, if you're using same material and you're printing above support, a lot of times, you're going to have a gap between that support, and that first layer above your support isn't really going to be very dense. And so above that, what you can do is you can use this gradient infill to really get a much denser surface a lot earlier than you would in a standard print. So essentially what we're doing here is we're eliminating all these weak points in the parts. We're removing all those areas with the porosity, and we're creating much more uniform mechanical properties in the parts. So if you take a look at this bar graph here, the two on the left, these are our solid parts that we tested, and the two on the right are the parts with sparse infill that we tested. And if you take a look at the The far left, so that's basically your solid standard print. In the blue, the 175.9, that's pounds of force we're showing there. And then the orange, that's our solid ADDCAAM part. And then the green, that's our standard part with the sparse infill. And then the light blue, that's our ADDCAAM part with the sparse infill. So now both of these scenarios, we saw that at least using ABS carbon fiber, that we're getting up to 60% stronger parts in both of these scenarios. So it's an extremely high increase in strength in comparison to a lot of the other ways that people are trying to increase the strength of these parts. And another real interesting thing I did, if you take a look at this image on the bottom right, I used an IDEX printer to print 2 different colors on every other layer, and then we cut the part in half and looked at it under a microscope to see, what that actually looks like after it's printed. And you can see the sort of structure that's generated from this. And I thought that was really interesting how it came out. So I figured I'd share that image as well. And it sort of shows in real life, how there's very little porosity inside of these parts, if any at all. So as far as opening applications, or I guess increasing the number of applications that you can use FDM parts for with this technology, the low porosity is one of the big factors that is going to really open up new applications for these FDM parts, things that you need to be watertight or airtight, things like ducting or pneumatics, things like that. And also even things like dielectric properties and stuff, because if you print parts that have voids in them, it's very difficult to control those properties. And then, of course, balanced parts, or predicting the amount of the weight of a part, because if you've got a part that has very homogeneous and very dense and low porosity, you're going to be able to predict the weight of your parts a lot better as well. Some more applications, just based on the increase in strength of the parts, So what this does for us is not only does it increase the strength to weight ratio, it's also increasing the strength to size ratio. So obviously, strength to weight is really good for things like anything that flies, aerospace applications, any sort of like protective gear or prosthetics or casts, things like that, really to make patients like more comfortable, or if you're wearing a helmet, not having some real heavy thing on top of your head. So it really opens up a lot of new applications there. Now, as far as reducing the size of components, if you have a lot of space constraint in the design of your part, if you've got a really complex assembly and you're struggling with fitting parts in there, if you can make your part smaller and still have the same strength, then that opens up a lot of possibilities there as well. So I believe that's the end of my portion of the, well, actually, you know what? I do have a video that I wanted to show before I pass it on to Jeremy of the testing that we did on our UTS machine. So we've actually got a tester, and we've set up a little rig to test these parts that'll show, the amount of force that they're able to withstand. So in this video, you're going to see that side by side, the standard part's going to be on the left, your ADDCAAM part's going to be on the right. And if you take a look at the digital readout on the bottom, it's going to show you the pounds of force that these parts are withstanding. And there's a pretty cool little slow-mo at the end that shows the parts breaking. So I'm going to go ahead and play this for you guys. So there we go. Can't have fun without a little bit of destruction, right? So I'm going to go ahead and pass it on to Jeremy now.
All right, thanks. So I'll tell you a little bit about REALvision Pro. We have a slicer called REALvision Pro that is basically state-of-the-art into slicing technology. We've been developing core features for the last 15 years, and it's really state of the art. And we have the ability to bring other capabilities through plugins. So that's what we've done for ADDCAAM, and I'm going to show you how we did it. One of the big question was, okay, how it's one thing when Dan and Addman is using the plugin, they are really experts, so they have no problem going into all those settings and finding their way through it. But to be honest, it's very difficult to use for a more normal user. So we are really wondering how to present this and how to make sure that people could use it. So a lot of the work has been into making this accessible. So I'm going to show you a video that simply show you how to get started with ADDCAAM. When you have the plugin installed, you can just turn it on.
Now I'm going to show you how to slice using ADDCAAM. So in REALvision Pro, you can open an object, and by default, the ADDCAAM plugin will not be enabled. So if you slice the object, hitting the prepare button, you will see a normal way of slicing. So the beads will be in the same plane. So if I zoom here, you can see that those are aligned. Now, how to enable the ADDCAAM plugin? Well, you go back to the normal view. In the main view, on the top right, you will see your plugin icons, and one of them is the ADDCAAM plugin. So when you click on this, you will now see ADDCAAM plugin and slice with ADDCAAM. This you can toggle on and off. So it means you can turn on your ADDCAAM plugin and now hit the prepare button to reslice using ADDCAAM. When you slice using ADDCAAM, now you will see that on the cross section, the beads are now using the ADDCAAM plugin. So you have shifted beads in the contour and also in the infill. You can also turn it off again by just clicking the toggle button.
So pretty easy to turn it on and off. I will show you in the order in which we've developed the ADDCAAM plugin, and now I'll show you a good utilization of this of the contour. So if you crank up the number of contour, then you can work with high strength, which is very useful for parts that are like 2.5D type of parts. Yes. So another thing that Dan mentioned is that when you are using ADDCAAM, since the beads are shifted, you actually create more space, and you are able to fill more material to it. So we actually added also a material flow setting that allow to play with the overflow. So this is very related to your configuration. But you can see on the left of this picture, if you have a configuration that are often in 3D printing, you reduce basically the flow for printability. That creates even more porosity. So you can actually end up in that situation where you do see the porosity. And then you can play with this overflow factor to make sure that your part is completely dense. So that's it for the demo. I'm really excited that we are now launching this plugin, and there's been a lot of discussion also on how should we make that available to as many people as possible, and a lot of discussion around the pricing. So I'm going to show you now what we were able to do to make sure that a lot of people could access it. So you can go to REALvision Pro. And for $20, so $19.90, you can actually get the slicer and the ADDCAAM plugin. This includes 2 seats, so it's a single user license with 2 seats. It covers everything that is in the slicer plan and has all the feature that we have described into this presentation. Right now, you can actually use it 14 days completely free. And we invite you to go and try for yourself on the website of REALvision Pro. Yes, the webinar is finished. We are now going to go into the Q&A session. So I will try to read the question. how can we address residual stress delamination issue through pass optimization? You want to try to answer this one, Dan?
Actually, you know, that brings to mind another feature in REALvision where we can actually control the direction that it's printed. I forget the name of the feature, but I think this was actually used. It's a feature for DED, actually, that we wanted to test out. And essentially, you know, it involves defining which direction that we're printing the outlines in order to sort of reduce that residual stress in the part, to reduce warping, delamination, etc. I
Yeah,
have
we do
not
have.
really experimented much with plastics on that, though.
No, there is a case where it's really. I mean, of course, if you start printing with engineering plastic, then you have cases. We also have worked a lot with FDM metal, where you have metal powder loaded into
Yeah.
plastic, where you print on a, let's say, standard FDM printer, and then you sinter the part and end up with a full metal part. And with this technology, it was quite important. It seems that there's the residual direction within the bead on which you print. So we've developed a feature to be able to alternate the direction of the print, so that on one slice you will do in clockwise, and then on the next slice you will do counterclockwise, and like this the force could balance out. So when you do the sintering, when you print the part, you will not see any defect, but when you do the sintering, you will start to see certain rotation. That completely eliminated that problem. We have another question here. Is the slicer optimized for FGF, granular industrial printer with 1 to 8 millimeter nozzle? So
I can attest to that. I'd say absolutely. Yeah, we've got actually 3 3D Systems Titan pellet machines. Those go anywhere from a 0.4 nozzle all the way up to a 10 millimeter nozzle, and I've printed countless parts using ADDCAAM on those printers. So the answer is yes. Yes, you can absolutely use it for those sort of larger scale printers. In fact, you know, you can actually create your own custom printers inside the software, and as long as the printer takes G-code, then you can use ADDCAAM for it.
So I think everybody just ran to the REALvision Pro website and is now trying to download and try. Just for information, we have also made sure to support a lot of the low-cost printer. So we've added a lot recently of the cheapest printer, just to make sure that that anyone could try ADDCAAM. So I think we added the Bamboo Lab, and yeah. So just to give you an idea of the price range that we are talking about. Yes. So I think that's the end of the webinar. I hope that this really gave a good idea of what we've done. If you are subscribed, you will get a link where you are able to watch it again, and we will find also we will put more information in terms of where to find the software, but it's REALvision.pro. But otherwise, you will receive an email after this webinar is ended. Thank you very much, Dan. Thank you for helping on this. It's been a great collaboration.
Thanks everyone for joining.